Hello everybody. For this video, we're going to talk about infinity and limits involving infinity. Now, infinity is a very interesting concept, and it's not really something that you would talk about anywhere else um, as soon as you pass the 5th grade, I suppose, because way back then, you talk about infinity a lot as if we knew what we're talking about. Anyways, mathematically, infinity is defined as something that is bigger than all possible numbers, right? All possible real numbers, that is. Or in the term of negative infinity, we're talking about something that is smaller than all possible real numbers. What that means, though, is infinity is not a number, right? Both infinities, the positive and negative infinities, they're not numbers. They're not in the same sense as numbers. They're more as directions if numbers are locations on the number line, right? If you think about. Now, infinities can be involved in limits in 3 different ways, right? The x value, the approaching, could be infinite. This right here could be infinite. This is what we call infinite variables sometimes, and this does happen in real life. A lot of time we assume time is infinite, right? Majority of times, though, we assume something is infinite even though it's not really infinite in some sense, right? For example, grains of sand on the beach. It's not really infinite, but it's large enough that we consider that infinite. Same thing, right? Atoms in the universe, not infinite. It's actually relatively small amount. If you think about the atoms, it's everywhere. It's made of everything. It's relatively small. It's actually a lot of mathematical concepts are much larger than those kind of numbers. However, we assume them to be infinite. Distance of the universe, again, observable universe, maybe not exactly infinite, but it's far enough that it might as well be infinite. In fact, we don't even know what's outside of observable universe. The point here is we're going to take those variables and assume those can reach infinite. So to abbreviate that, we say those are infinite variables. On the other hand, we could have x approaches to a finite number, but the result is positive or negative infinity. This right here, right, we talked about previously is what we know as a vertical asymptote. Again, we'll define that in a little bit, redefine that a little bit, but we know that is a vertical asymptote. This just means the graph is approaching to a line infinitely, right? It's going up forever, we're going down forever, getting closer and closer to that line, but never really able to, intersect or cross the line. Well, the last thing is, well, for both the variable and the infinite function. Oh, by the way, this oftentimes is called infinite function, where the function approaches infinity. It's really not that exciting of a thing. Most functions are infinite functions as you choose a large enough value or a value that's close to the vertical asymptote. The last case is both infinite variables and infinite functions. There's four possibilities here. We'll see some of that, and again, most functions actually behave like this, right? Especially most polynomials behave in certain form of this kind of behavior, right? If you make a big enough number, your output is going to be pretty big as well. Anyways, let's see some graphic interpretations of these kind of limits. Here we have this graph. You don't really need to know what the actual graph is, the function of the graph is, just from the graph itself, where we can tell everything we needed. The red is the graph, so let's take a look at the these limits here. The first one is limit as x approaches to -2 from the left. So I'm moving towards -2, but I'm approaching it from the left. So I'm following along this curve. Right, I'm following along this curve. As you can see, the curve shoots up, almost getting as close to 2 as possible, but you never reach -2. So you are just going to continuously to go up infinitely. So this is going to positive infinity. Similarly, if now we approach negative 2 from the right, you have to follow along this curve, right? Because we're going now this way. You're approaching to negative 2 from the right. So you kind of go down infinitely. So you're going to negative infinity. Well, what that means, using our definition from last class, right? Approaching from the left, I go to positive infinity. Approaching from the right, I get to negative infinity. So the prediction is not the same from both directions. So in this case, the limit is does not exist, right? The limit is d and e for the limit approaching to negative 2 from both directions, just because we can't agree on what it actually should be. Similarly for d, for x approaching to 1 from the left, I'm going towards 1 from this direction. So I'm following the curve going upwards, right? Shooting up infinitely, right? So the answer is infinity. And then if I'm approaching to 1 from the right, I'm approaching to 1 this direction. So I'm following along this curve here. Then the limit goes to negative infinity. Once again, the limit as x approaches to 1 from both directions does not match. So the limit is just d and e. Now, for g, right, this is where we're talking about infinite variables. For x approaches to infinity of f of x, well, infinity is basically that way, right? Again, infinity is more of a direction. So if I'm keep going to the right, it looks like my graph is just kind of, going to the right, but it's not going up infinitely. It's actually approaching to that line right there, right? Later on, we'll define that as a horizontal asymptote, but we're approaching to that line right there. So the limit is actually going to equal to 1. Similarly, for h, as x approaches to negative infinity, right? Negative infinity, again, is just more of a direction. So I'm going to the left forever. So I'm following along this curve, but I'm still approaching to that line there, right? I'm just getting closer and closer to that line. So the limit is also equal to 1. Last but not least, just for the lulz, right? Even if you have this weird looking graph that has 2 vertical asymptotes, what happens if you're taking a limit as x approaches to 0? Well, 0 is actually not any of the asymptotes. So 0 is just right here, which on this part, the graph is continuous. So to get this limit, all you have to do is plug that into the function. So all you have to do is say, hey, look, this is equal to f of 0, which means plug 0 into the function, you get 0 squared minus 3 over 0 squared plus 0 minus 2. So your answer is just simply 3 over 2, right? Negative 3 over negative 2, but the negative cancels out. Yeah, so it's a very easy limit to do. Basically, even though we're dealing with a function that's not continuous everywhere, that has some missing x value as a domain, these type of functions, this is called a rational polynomial. Rational because they're ratios, they're fractions, right? And polynomial because numerator and denominator are polynomials. Rational polynomials are continuous on their domain. That is, the only problem is their vertical asymptotes. Okay, so still pretty nice, still fairly well behaved. So we still like them. Okay, so for the majority of this section, we are going to be focusing on this, and then towards the end, we'll move away from rational polynomials. Okay, let's take a look at one more example. Why not? Example 2 is a slightly different graph. We're going to do this a little bit quicker here. For x approaching to negative 1, if you want, pause the video and try these yourself, right? But for x approaches to negative 1 from the left, I'm going this way. So I get positive infinity. X approaches to negative 1 from the right, I'm going this way. So following the graph, I'm going down. So negative infinity. And because they don't match, limit as x approaches to 1 from both directions, d and e. For D, x approaches to 1 from the left, so I'm going this direction, so I'm going down, goes to negative infinity. And then as for E, as x approaches to 1 from the right, I'm going to this direction, right? So I'm going upwards, positive infinity. Unfortunately, once again, they don't meet up, they don't agree with each other, so they go their separate ways, and we can't agree on it, on the limit. So limit D and E. For G, as x approaches to infinity, so as x value goes to the right, I follow my graph, and it looks like it's approaching to that line there again. So approaching to 2, right? The line y equals 2. Similarly, for H, as I goes to negative infinity, I'm going this way forever, and I'm following along the curve, approaching to that line right there, so also equal to 2. And again, just for the laws, right, as g of h approaches, as x approaches to 2 for g of h, 2 is right here, right? The value is right here. Or what that means is you just simply plug in g of 2. So I'll just write down here. G of 2 equals to 2 squared plus 1 all over 2 squared minus 1. That's equal to what? 8 plus 1 over 4 minus 1. So 9 over 3, which is 3. So this is just 3. So again, rational polynomials are continuous on their domain. So anything that's not part of the vertical asymptote is really not going to give you any issue whatsoever when you take the limit of it. Just simply plug and chug. Oh, also known as the direct substitution method. Anyways, let's go ahead and define some terms, right? Now, formally, we're going to go ahead and define f of x has a vertical asymptote at x equals to a, provided we can kind of see the pattern here already. We say that, hey, look, this is a vertical asymptote at -1. What happened at -1? Well, the limit and as x approaches to -1 give me infinity or negative infinity. Okay, same thing with positive 1, right? Again, that's going to give us infinity and negative infinity and infinity. So if you have one of these cases, then this particular value of x is said to be a vertical asymptote. In other words, f of x has a vertical asymptote at x equals to a, provided either limit as x approaches to a from the left equals to plus or minus infinity, or limit as x approaches to a from the right equals to positive or negative infinity. Either one of these 4 cases is sufficient to say that f of x has a vertical asymptote at this value. Similarly, f of x has a horizontal asymptote at y equals to b, right? Horizontal lines have to be written in terms of y equals something. Same thing here. We simply evaluate the limit at infinity. And there's really 2 infinities here. So limit as x approaches to infinity, f of x equals to b, or limit as x approaches to negative infinity, f of x equals to b. Okay, so that's the two formal definitions for horizontal and vertical asymptotes. Now, of course, you might have seen some other definition previously. They are essentially equivalent, but these are the formal definition. In fact, there's some kind of gnarly thing here at play. If you are strict by these definitions, there are some interesting counterexamples that you might see if you follow these definitions compared to the the old traditional ones. Anyways, this is the one that we're going to be working with. Now, very important here, we can see that the graph of the function never crosses the vertical asymptote. Or cannot, really. That's the word I'm having you fill in. But it can cross its horizontal asymptote. We kind of see that here. For this particular example, for example 2, it does not look like it crosses the horizontal asymptote, right? This is the horizontal asymptote here. But for this example, it does cross the horizontal asymptote. Like, there's a cross right there, and the cross could be elsewhere as well, right? So the graph can cross the horizontal asymptote. There's no definition that restricted from it. In fact, if you're working with a piecewise function, again, it has to be piecewise, the vertical asymptote can be crossed as well. But it has to be piecewise. In other words, it has to be built to cross that vertical asymptote. So when we say a function, we mean a standard function cannot cross a vertical asymptote. Okay. This last part is actually kind of important as well. The horizontal asymptote are often referred to as the end behavior of a function. So in behavior, again, think about think about the variable, right? The infinite variable uh, in terms of time. Basically, what you're saying here is whatever function you're working with, as time goes on forever, right? As time goes on to the end of time, so to speak, how would your function behave, right? This is important in a lot of different aspects of of real life. For example, in a system, right, in a region, the population of say a specific type of animal, like a rabbit, um, it doesn't grow forever, right? Because you're restricted by say the region's resources, the region's predators, right? The region's weather, like all of that, it restricts how much of a population you can have. Um, so even if you leave the region, alone, if you impose no man-made restriction on the population, it doesn't just grow forever. There's a there's always things that's going to prevent your population from blowing up, from going to infinite, and eventually your population stabilizes. So that's kind of what we're talking about, right? As time goes on forever, your population, is going to be revolving around this a stationary amount. So that's what we mean by in behavior of the function. So we see the graphic interpretation of limits. Majority of times, though, we are going to be dealing with limits algebraically. So let's go ahead and take a look at some of these problems. So how do we find the asymptote of a rational polynomial? We're going to go ahead and use this notation: f of x equals to p of x over q of x. P of x is pretty standard for polynomial, and q just happens to be the letter right after. So if you're using two polynomials, pretty common to use p and q. The point of this notation is just to say that, hey, look, then I can just name the numerator and denominator without writing down these super long words. Okay, these are pretty long words. Anyways, so recall from the first class, if we apply the direct substitution method and you get, for this limit, and you get 0 over 0, then that means there's a factor on the top and a factor on the bottom that we can cancel out, right? And in that case, you should cancel, and then you move on to the next step. In other words, if you get 0 over 0, you can't just call it a day. You kind of have to do some cancellation first, and then you come back to re-tackle these kind of problems. What that does mean is if you cancel, right, if you have your cancellation, if you made your cancellation already, and then you plug in x equals to a with the direct substitution method, and you get a non-zero number over 0, then we know that the limit does not exist, right? The limit does not exist. But this right here is an indicator that we're dealing with a vertical asymptote. Directional limits, if you allow infinity to be a valid limit, will always exist, okay? But technically, infinity, because it's not a number, we don't always count infinity as a valid limit. That's why we say the limit D and E. Okay, so in the previous example, like for example here, when we say that the limit is equal to infinity, right? But infinity is not really a number, so in this case, we can still say that the limit doesn't actually exist. It just kind of goes as big as we want it to be. That's what this equal to infinity means. Okay, in case you think there's a little discrepancy here, but it's just a matter of interpretations at this point. Okay, so basically you plug in the value x equals to a, and you realize you get non-zero number over 0. That means we're dealing with a vertical asymptote. What do we do there? Well, we can actually identify the vertical asymptote first, right? If your function's f of x equals to p of x over q of x, all we have to do is just like defining the domain, right? All we have to do is set the denominator, which is q of x, to 0. But we have to double check that the zeros of q of x are not the zeros of p of x. In other words, the numerator, right? Otherwise, you should cancel it first. So here's an example. Find the vertical asymptote of this function. And one of the best things you can do here is simply to factor, right? So x minus 3 on the top, and then the bottom factors into x minus 3, x minus 2. It's always a good idea to practice some factoring. If you need some help with that, come and look for me. I'd be happy to help you. Okay. At this point, basically, we set the denominator equal to 0 to see what happens, right? So set x minus 3, x minus 2 equal to 0. And we can leverage the zero divisor property. We set that equal to 0, x minus 3 equals to 0, x equals to positive 3. That's my first possible vertical asymptote, right? Set that equal to 0, x minus 2 equal to 0, x is therefore equal to 2. My second possible vertical asymptote. Now I say possible because, again, you have to double check, right? So for x equal to 3, unfortunately, if you plug in f of x, x equals to 3 into f of x, so you get f of 3, you're actually going to get 3 minus 3 over 3 minus 3 times 3 minus 2, and of course that's going to give you 0 over 0. So it turns out, right, it's really not a surprise here, that the 0, that the x equals to 3 is also a 0 of the numerator. So in this case, x equal to 3 is not a vertical asymptote, right? This is a removable discontinuity. It's not, there's a hole there, right, on the graph, but it's not a vertical asymptote. So this is not it. So let's go ahead and cross that out. Now, we're just gonna play along here. Go ahead and plug in the 2 as well. We get 2 minus 3 over 2 minus 3, times 2 minus 2, and that's equal to negative 1 over 0. So this one is, we're good to go here, right? So x equals to 2 is the vertical asymptote. Okay, and you have to write your vertical asymptote this way, right? X equals to a number indicates a vertical line. Okay, x equals to a number indicates a vertical line at that number. So you have to write it this way. Okay, moving on to the next one then. Next question. Now that we know x equals 2 is the vertical asymptote, right? How do we evaluate the limit at the vertical asymptotes? Basically, again, once we do the direct substitution method and we get the keyword here is non-zero over 0, we have to apply, I like to call point testing. Okay, point testing. What that means, though, is I want to test values that are very close to that said vertical asymptote. I want to test values because I don't know whether my limit is infinity or negative infinity. So let's take a look at this example again, right? As x approaches to negative 1, from the left, we get positive infinity. From the right, we get negative infinity. But if you flip that around, if you focus on x equals to 1 here, it's flipped, right? From the left, it is negative infinity. From the right, it is actually positive infinity. The point here is you don't actually know how the function is behaving. And without the aid of a graph, we have to find a way of testing for this algebraically. And really, the easiest way is to test for points that are 0.1 away. Now, the closer the better, right? The closer the more significant, but 0.1 I found is usually good enough. No function is typically going to give you two vertical asymptotes that are 0.1 away from each other. That's usually a little tedious to deal with. So 0.1 is good enough. So basically here, let's take a look. For part A of example 4 here, I'm doing as x approaches to 2 from the left. And we know from the previous example that x equals to 2 is a vertical asymptote. So, we don't have to bother plugging it in for this particular problem. So if I'm working with approaching to 2 from the left, we want to use the number minus 0.1. So here I want to test x equals to 1.9, right? 2 minus 0.1 is 1.9. And when I say test, all I mean is simply plug that into the function. So f of 1.9 equals to 1.9, 1.9 minus 3 over 1.9 squared minus 5 times 1.9 plus 6. Okay, and it looks like that is negative 1.1 over that 1.9. Well, I guess we can punch that into the calculator here. I have to do this off screen now, so 1.9 squared minus 5 times 1.9 plus 6. Looks like I got 0.11. So negative 1.1 divided by 0.11 is equal to negative 10. Not too bad. Let's see, double check that. Okay, yeah, good. So I get negative 10. So what does that negative 10 tells me? Well, again, remember my answer is either positive infinity or negative infinity. So what do you think that negative 10 should imply? Well, should imply I'm going to negative infinity. Okay, that's really all there is to it. So not too challenging of a problem here, but we can actually make this even better, right? Even easier. Two ways to do that, and really the simplest way is instead of struggling to plug in like I did here, right? Plug into the original function, the factor form is actually easier to plug in, right? Even I can do it, right? So let me show you what I mean here. So for part B, I'm approaching 2 from the right. So approaching 2 from the right, I'm using the 2 plus 0.1. So I'm actually testing for x equals to 2.1. Now, if I just plug into the original function, right, I'll have the same issue, right? I then have to, bust out a calculator to get the right answer. But if I use the factored form, I already factored this before, so x minus 3 over x minus 3 x minus 2. In fact, if I want to make my life really easy here, I can go ahead and cancel. But let's suppose you don't have cancellation here, which sometimes it could happen. So how do I plug this in? The factor form is really nice because ultimately we only care about positive or negative output. We don't care about exactly what it equals to, right? So I can just plug it into this factor form and get this 2.1 minus 3 over 2.1 minus 3 times 2.1 minus 2. And because I only care about positive or negative, that's all the question I'm going to ask. 2.1 minus 3, is that positive or negative? Well, that's negative, right? Because 2.1 is smaller. 2.1 minus 3 here, again, negative. 2.1 minus 2, that's positive. So here I got a fraction that's negative over negative times positive. So altogether, this fraction is what? Positive, because the double negative cancels out. So here, my limit is positive infinity. That's really all I have to do. So see, I can do this without a calculator, assuming that I can factor the polynomials. So again, guys, factor is really, really important for this kind of problem. Now, last but not least, part C. Once again, we got one positive and one negative limit. Therefore, the limit cannot agree on each other. So the limit D and E as x approaches to 2 from both sides. Okay, so that's basically how you want to tackle this kind of problem. Now, this does mean we have 3 possible cases, right? If you basically do this point testing, this point testing technique, if you get both of the limit to be positive, so positive is positive, then the final limit actually equals to infinity. If both give you negative and negative, then the final limit actually equal to negative infinity. And then case number 3 is the situation that we have here, is where you get one positive, one negative. You don't really care about which one's the positive, which one's the negative, as long as you get one positive, one negative, then the actual limit is D and E. So this one does come into a couple of separate different parts, and you will be able to see that on some of the homework assignments. But each part is fairly easy. So just remember, point testing is whenever you plug in a number and you get non-zero over 0, right? That's the key indicator here. Okay, so that's it for the vertical asymptotes. Let's move on to the horizontal asymptotes. And again, horizontal asymptote, because the definition, right, as x approaches to positive infinity and x approaches to negative infinity, so a function can have up to 2 horizontal asymptotes. But rational polynomials can only have one, and can only have one. You'll see kind of why later on in the as we progress. But this is also a very easy step, right? Very easy task. A lot of time you can actually look at the answer, look at the question, and tell me the answer right away. But we gotta build up to that. Okay, so let's start with a couple of easy limits. For a function such as 1 over x, as x goes to infinity, remember this is the infinite variables here, right? So kind of as a quick example, right? If you got one large pizza, that's what this one means, at this point. If you got one large pizza and you share it among no one, right? You just eat it for yourself, right? It's like me, this typical Tuesday night. You can have the whole pizza. But as x increase more and more, right? We tell your friend found out about you have this pizza, and they invited themselves over, and then all of a sudden, they start inviting other people over, and next thing you know, your apartment is full of 17 different people. Well, your pizza that you're gonna get is gonna get divided, right, more and more, and each person, assuming some sort of fairness, because you're too kind to say no, um, you're all gonna get smaller and smaller and smaller pieces of pizza, okay, until somebody made a post on their fraternity page, and all of a sudden the whole fraternity shows up to your apartment with like a couple of thousands people, and then you'll be lucky if you even able to touch the grease of that pepperoni. So as the number of as x increase, right, as the number increase for the denominator, the whole fraction becomes smaller and smaller and smaller and smaller until it approaches 0. So 1 over x as x goes to infinity is simply equal to 0. And I think you can kind of play along the line here with the next couple of examples, right? In the next 2 examples here. This one, the following part B here, our function is 1 over x cubed. So the denominator is actually increasing even faster, right? So even if x is equal to 10, I'm dealing with 1 over 1,000. So this also equal to 0. And of course, if you follow the same logic, this actually works for any power n, and that's also going to equal to 0. So 1 over n to the any positive power is going to equal to 0, no matter what power that is, as long as it's positive. Well, it has to be positive, otherwise your fraction gets, flipped upside down, right? So that's no good. But it has to be positive, okay? But it could be whatever you want. It could be a fraction. You could be a radical. You could be any large exponents, right? It doesn't matter. Your limit is going to be equal to 0. So, with that in mind, the technique for rational polynomials, again, rational polynomials means P and Q are both polynomials. The technique for this is you divide the numerator and the denominator by the highest power of x in the function. So let's take a look at this example. I'm going to write this out. Oh, here, I'll tell you what. Divide is another way of saying multiply by 1 over, right? 1 over, I'll put 1 over x for now, but let's decide what's the highest power of x. Well, I got a power 3, this is a power 1, this is power 2, power 3, this is power 0 here for the constant term. So the highest is actually 3. Well, that's what I'm dividing it by. Okay, so first step is dividing by 1 over x to the third, and that allows me to distribute. So this is limit as x approaches to infinity, 4x cubed over x cubed minus 2x over x cubed all over 5x squared over x cubed plus 3x cubed over x cubed minus 7 over x cubed. And we're going to go ahead and do the simplification here. So limit as x approaches to infinity, I just have x cubed over x cubed, right? That goes away. So I just have 4 minus x cubed and x third. They cancel a little bit. I get 2 over x squared. And then on the bottom, I have 5 over x plus 3 minus 7 over x cubed. Now, the beauty of limits is I can actually evaluate these limits individually. Okay? Evaluate the limit individually here. So what that means here is I can basically apply what I just talked about, right? What I just learned, but to each one of these terms individually. So that's going to give me, well, limit of any constant number is just that constant number, right? We were talking about this the other time. So this is just 4. And then 2 over x squared, right? Basically, same thing, right? So what if you got 2 pizzas? If you're sharing among 1,000,000 people, you're still going to get 0. So minus 0 over, on the bottom, 5 over x, same thing, right? What does it matter if you have 5 pizza, right? You're still divided by 1,000,000,000 people. You're going to get 0. And then plus 3, and then, well, 7 pizza is not going to help you either. So you're going to get 0. So ultimately, the answer is actually here just 4 over 3. Okay? Very simple concept, but the first step takes a little bit of extra work just to kind of write that down. Okay? Now, this method is pretty strong. It's actually pretty universal. It's strong enough that it doesn't only work for rational polynomials, It works for a little bit of radical as well, but it takes a little bit of algebra and a little bit of extra manipulation. So we're not going to deal with that too much. But this method makes rational polynomial questions really, really easy. And so easy that if we kind of remember the following couple of cases, right, the following 3 cases actually, then we can look at the answer, look at the question and tell the answer almost immediately without any work whatsoever. Now, you can remember to do both, right? Obviously, example 5, I gave you a way that you can apply without having to do, any sort of extra memorization. But the following cases are so nice, I strongly advise you to remember this and make use of it. Okay, I'll even explain part of the reasoning for this too. So the first thing I do want to remind you here is this notation of degree, right? This DEG, um, degree of f. This is known, degree of f of x. Okay, just to remind you what that notation means. Degree of a polynomial. Oh, I have degree of f here. Degree. I should use p and q here. Sorry. I will upload the right version, the right notation, the right letters version, um, hopefully on your notes. Anyways, so here the basically f, I'm using f for the numerator and g for the denominator. Okay, so my yeah, I have a wrong notation here, but the rational polynomial should look like this, f and g. Okay, so the degree of a polynomial is just the number of the highest power in that power of x in that polynomial. So let's take a look at some of these examples first, okay, just for practice. For the first function, right, for f of x, the numerator, the highest power of x is just that 1 there. So the degree of the top is 1, and then the degree of the bottom is 3. For part b, the degree of the top is 3, the degree of the bottom is 2. Last but not least, for part c, the degree of the top is 2, and the degree of the bottom is also 2. Okay, so that's just degree, just another way of saying the highest power of x, the number of the highest power of x inside a polynomial. Okay, so you got 3 cases. If the degree of the top is less than the degree of the bottom, so instead of using f and g, I'm just going to say top and bottom, just to try to avoid any sort of confusion here. But again, f is top, g is bottom. Okay, so if the degree of the top is less than degree of the bottom, then automatically your horizontal asymptote is y equals to 0. Quick and easy. So that is actually this case right here, right? For part A, degree of the top is 1, degree of the bottom is again 3. So in this case, limit as x approaches to infinity, f of x just equals to 0. There's not much you have to do. Case 2, if the degree of the top is greater than degree of the bottom, so degree of f is greater than degree of g, then again automatically horizontal asymptote b and e. Or if you want, you can put infinity, but preferably b and e. That is the situation for part B, right? The degree of the top is 3, degree of the bottom is 2. Degree of the top bigger than degree of the bottom. So here, limit as x goes to infinity, g of x again, you can put infinity, but here preferably put d and e. Preferred. think there's only one R in there. Oh well. Last case, if the degrees are the same for top and bottom, then you kind of have to write this out. Y is the ratio of the leading coefficients. What does that mean? Well, coefficients, the leading coefficient is the coefficient where the number multiplied to the highest power of x. So for part C, right, we see that the degree for top is 2, degree for bottom is also 2. So it does falls under case 3. And then the leading coefficient, right, is the number, the coefficient right before the highest power of x. So for top is 3, and for bottom is 5. So in this case, limit as x approaches to infinity, h of x simply equals to 3/5. Very straightforward answer if you remember the cases, right? If you remember the cases. So if you don't want to remember these cases, that's also okay. Then just apply the method we talked about in example 5. Okay? Either way, you have a choice. I strongly suggest you to remember the cases. Just, can help you do this kind of problem a lot quicker. Okay. So that is the this case, the simple case of horizontal asymptote rather, or limit at infinity. We do have a couple of more problems. We're really the 2 more problem types that you're going to be dealing with. One of them is radical functions. Radical functions, especially the subtraction version of radical functions, it's always going to be subtraction version, mainly because in terms of limits, we have a type of limit called the indeterminate form. So let's take a look at, go all the way down real quick here. I just want to kind of mention these. There are things that we can tell the limit right away. Infinity plus infinity, that's just infinity. There's no way around that. However, infinity minus infinity is what we consider indeterminate, because it could be anything between any real number, and you cannot have a good way to decide about that just from the sheer information of infinity minus infinity. Okay? Infinity times infinity, good, that's just infinity, right? Big times big just equals to super big. Nothing crazy about that. 0 times infinity, that's indeterminate. Well, because 0 indicates small, infinity indicates big, right? Infinity, big times small, you don't actually know which one's more effective. Maybe the small is more effective, right? I mean, here's an analogy: will be like you have a strong man on the side versus a heavy object. Can the strong man lift a heavy object? Well, it depends on how heavy this object is, right? To some people, lifting 100 pounds might be heavy, or maybe even 300 pounds. Well, the strong man can lift it maybe fairly easily too. But if this heavy object is like 25 tons, well, this is strongman Spider-Man, right? You're not going to be able to lift that. So like the interaction of big and small in terms of multiplication definitely depends on how the interaction is going. So 0 times infinity in terms of limits is also indeterminate. The last one, 0 divided by, the last set really, 0 divided by infinity, that's just 0. It's really nothing, no argument there. On the top is going to 0, on the bottom is going to infinity, which also implies going to 0. So nothing's fancy here. However, 0 over 0 or infinity over infinity, that's indeterminate. And we know the first one already, right? So if you got 0 over 0, chances are you got to do some algebra, and we can easily set up problems where once you get 0 over 0, and you cancel, you can set that up so that the limit could be anything you want it to be. Okay, And it's actually the same idea with infinity over infinity. You can set it up in a way that the limit is whatever number you want it to be. So here, both of these cases are indeterminate. So very similar things, but have drastically different outputs, right? Different outcomes. That's what we're relying on for the last two problem type. For this problem type, for the first one, it was radical function. The way you want to do this is to multiply and divide the function, right? This whole thing here, by the conjugate radical. Conjugate radical. The conjugate is where you have the same terms, but the inside sign is flipped. So that is square root of f of x plus g of x. The beauty of that is we can leverage the uh, difference of square formula. So just to kind of remind you here, a squared minus b squared equals to a minus b times a plus b. The subtraction, right? Of course, that's the difference of, and a squared and b squared, so squares. Yeah, so that's the difference of squares formula. That's why we wanted a minus sign and a plus sign, right? So that minus, so this minus and that plus combined together, we get those squares, right? On the left hand side, the a square and b square, and we want that because the square is gonna get rid of that radical. Okay, that's the goal of this, right? That's the kind of the concept behind this. So let's take a look. When you're taking this limit, right, again, this falls under the form of the radical f of x minus g of x, right? In this case, f is x squared minus 2, and g is just x. Fairly simple here. So let's go ahead and actually let's see why this is a problem first, right? So if you take x goes to infinity, right? If x goes infinitely big, this part on the inside also becomes infinitely big, and the radical doesn't actually slow it down either, right? Like, I mean, it slows it down a little bit, but not by much. You are still going to be infinitely big. So you got infinity here, and then minus, as x goes to infinity, well, this obviously still goes to infinity. So you have the problem with infinite minus infinity, right? Which we knew was indeterminate. So we got to do something about it. So here's the technique. We want to multiply on top and bottom, or multiply and divide, which is multiply on top and bottom, by the conjugate radical. So x squared minus 2 plus x over the same thing. When I multiply and divide by the same thing, I'm not changing the question, right? I'm changing the looks of the question, but not changing the question overall, because that's just multiplying by 1. But what that does is that the numerator becomes a difference of square, right? This difference of square formula. So I just have the first term squared, so square root of x squared minus 2 squared, minus the second term squared, so x squared, all over. On the bottom, you just kind of leave it as is. So radical x squared minus 2 plus x. Okay, so this is what you get. And again, that's the whole point is we set up to this step, because then the radical cancels out. Limit as x goes to infinity, the radical and the square cancels out. You just have x squared minus 2, and then minus x squared on the other term, all over square root of x squared minus 2 plus x. And now the numerator, right, we have some cancellation. So I'll write it down one more time just to show you all. X squared, actually, let me do it this way. the x squared and the x squared cancels out. You just have -2 on the top. On the bottom, you just still, nothing's really happening here. Okay, you just have that. Now, it doesn't necessarily look super good compared to the original. In fact, it almost looks like this is worse than the original, because remember, this is the original, right? But what do we actually gain from this? Well, the problem with the original is that minus. That gave us the infinity minus infinity, which we knew was indeterminate. But what do we have here? Well, as x goes to infinity, this part, right, as our analysis said before, this part goes to infinity, and then plus the x part goes to infinity. But the good news here is what? Infinity plus infinity is just equal to infinity. There's nothing ambiguous about that. So this is actually equal to something like -2 over infinity here, right? This notation is a bit sloppy, but we'll go ahead and let that slide for now for this class. But basically, what we're saying before is I got -2 on the numerator, but then the bottom goes to infinity. So just like before, this equal to 0, right? When your numerator is just some number, denominator is infinity. Well, the whole fraction goes to 0 because it just gets smaller and smaller. And that's your final answer for this problem. Not too bad as long as you follow this procedure. Okay? Moving on to the last example for this video. The last example is kind of something that we already kind of experienced this, but this time without the radical. So, if we have a indeterminate subtraction, if we got infinity minus infinity, well, again, we want to rewrite that somehow into something else, right? But the ones I want to focus on is formatting like this involving, say, polynomials. Okay, so here the trick is factor out the the lowest power of x. The lowest power of x, then reevaluate. Okay, so let's go ahead and practice that. This one is fairly straightforward if you kind of know the steps, know the key here, which is the factoring part. So I have 5x to the 4th minus 3x to the 7th. Well, the smaller, right, the lowest power of x is the 4. So I'm going to take that out. So I get limit as x approaches to infinity. X to the 4th, I have 5x to the 4th. Take out the x to the 4th. I just have 5. Minus 3x to the 7th. Take out x to the 4th. I get 3x to the 3rd. So what I did here is I turned my subtraction into a multiplication, right? It's, x to the 4th times 5 minus 3x cubed. Doesn't seem like much, but what ended up happening here is if I evaluate my limit, right, as x goes to infinity, x to the 4th, right, obviously also goes to infinity because it's some bigger number. It's even bigger than the original x. But then inside this radical, I got this long number 5, right? It's just some 5, this number 5. And then I'm going to minus a expression that becomes infinitely big, right? Just focus on the 3x cubed part. It's going to become infinitely big as x becomes infinitely big. So you actually just have this 5 minus infinity kind of thing, right? Basically, if you got $5 and you got this friend of yours that infinitely borrows money from you, well, let's just say you're not going to have that much money left, right? Because these day and age, $5 is a lot. So 5 minus infinity is actually just going to equal to negative infinity. Nothing really crazy here. But once again, what that does is it turns infinity minus infinity, which is indeterminate, into infinity multiplied by infinity, which actually is defined. It's you know it's fairly easy to see. It just becomes infinitely big, right? The only thing extra here you have to consider is that extra negative, right? So all you have to do is put that in the front. Okay, so this function goes to negative infinity as x goes to infinity. That's it. So this is your final answer. Okay, so not too bad of a problem. It's just something that you kind of have to remember, on the side of exactly what to do. But ultimately, these two problem types is really not too difficult, and uh, I think I remember you had to do one problem for each on the homework assignment. So make sure you get started on that, and I will see you guys for the next class.